Astronomers revealed that they had pierced the veil of darkness and dust at the center of our Milky Way galaxy to capture the first picture of the gentle giant dwelling there. A supermassive black hole, a trapdoor in space-time. The image was released in news and conferences in Washington and around the globe, showed a lumpy doughnut of radio emission framing empty space. The first direct image of the gentle giant in the center of our galaxy. It seems that black holes are like doughnuts. In 2019, a team captured an image of the black hole in the galaxy Messier 87, or M87. That image, the first ever taken of a black hole, is now enshrined in the Museum of Modern Art in New York. Astronomy lovers, we have seen what we were unable to see. Understanding of gravity, galaxy evolution, and how even placid seeming clouds of stars like our own majestic pinwheel of stars, the Milky Way, can generate quasars, enormous geysers of energy that can be seen across the universe. Supermassive black holes are the energy source of quasars. A similar new picture of the M87 Black Hole was 1,500 times as massive as the Milky Way's. Typically in physics or astronomy, when something increases by a factor of 10 or more, everything changes. Such fireworks, quasars, can outshine galaxies by 1,000-fold. Their discovery in the early 1960s led physicists and astronomers to take seriously the notion that black holes existed. What gave rise to such behemoths of nothingness is a mystery. Dense wrinkles in the primordial energies of the Big Bang? Monster runaway stars that collapsed and consumed their surroundings in the dawning years of the universe? Since 1974, the center of the Milky Way has been known to coincide with a faint source of radio noise called Sagittarius A, pronounced Sagittarius A star. Astronomers had calculated that whatever was there had the mass of 4.14 million suns and was confined within a sphere the size of Mercury's orbit around the Sun. They reached that estimate by tracking the orbits of stars and gas clouds swirling about the center of the Milky Way and measuring their velocities at 1/3 the speed of light. A black hole's gravity will distort and magnify its image, resulting in the case of Sagittarius A in a shadow about 50 million miles across, appearing about as big from Earth as an orange would on the Moon. Astronomers ever since have been trying to sharpen the acuity of their telescopes to resolve the shadow of that orange. But ionized electrons and protons in interstellar space scatter the radio waves into a blur that obscures details of the source. To see deeper into the black hole shadow, researchers needed to be able to tune their radio telescopes to shorter wavelengths that could penetrate the haze. And they needed a bigger telescope. The data for Sagittarius A were recorded during the same observing run in 2017 that produced the M87 image, but with more antennas, 8 instead of 7. Because the team was able to include a South Pole telescope that could not see M87. The Milky Way's black hole is a gentle giant compared to the one in M87, which sends quasars shooting across space. It's only putting out a few hundred times as much energy as the Sun, despite being 4 million times as massive. And the only reason we can study it at all is because it's in our own galaxy. Our black hole was more difficult to observe than the one in M87 for another reason. At less than 1,000th the mass and size of the M87 hole, ours evolves more than 1,000 times faster, changing its appearance as often as every 5 minutes. On Thursday, May 12, 2022, Catherine Baumann, a team member and computer scientist at the California Institute of Technology, said that making a picture from the 3.5 petabytes of data from the observations was like listening to a song being played on a piano that has a lot of missing keys. Using a technique called very long baseline interferometry, the antennas in the network were paired off with each other one by one, like individuals shaking hands with everyone in a crowd. The more telescopes in the network, the more such handshakes can be performed and their results compared. Computer algorithms could then begin to fill in the missing data and simulate the possible structure of the black hole disk. If you like the video, please share the same with astronomy lovers and subscribe to our channel Secrets of Space for astronomy updates. Thank you for watching.